There are over 13 trillion possible paths to get from the start to finish on this graph, given that a traveler may travel in any direction except where he or she just came from. And yet, we can find the shortest path in a matter of minutes. This phenomena led us to ask ourselves, what is the best way to find the shortest path? We began by exploring the mathematical algorithm known commonly as the shortest path algorithm, Dijkstras Algorithm. This algorithm begins at the starting vertex, picking the unvisited vertex with the lowest cost. By calculating the lowest distance to its neighboring vertices and selecting the lowest cost, Dijkstra's algorithm will find the shortest path by repeating the process over and over again. The exploration of this algorithm led us to asking, how do we apply this algorithm to problems? But in order to apply it, we had to understand the sample space we would be working on, graphs.
First we have the cubic graph, where each vertex has 3 edges. Then we have the dipole graph, a graph of 2 vertices with any number of edges in between. The wheel graph is a graph of 1 vertex in the center and any number of vertices connected around it. Then we have the regular graphs, where every vertex in the graph has the same degree. A 0 regular graph has all vertices of degree 0. A 1 regular has degree 1, 2 regular of degree 2, and so on. We also have the tree graph. It has no cycles and each vertex is connected by exactly 1 edge.
Here's an application of Dijkstra's algorithm. First I see how far I can get in 1 move, then 2 moves, and so on all the way until I reach the end of the graph. If there is ever an instance where I can reach a vertex by avoiding a costly edge, I cross it out. By repeating these steps, I will find the shortest path.
While applying the shortest path algorithm to these graphs, we asked ourselves what are the most basic ways to measure the shortest path. We realized there are 2 basic ways to calculate a shortest path, by a brute force method and by a recursion method. Brute force method would involve measuring each possible path on any graph, then comparing their lengths. The problem with brute force method is as the number of vertices gets larger, the number of possible paths to measure gets exponentially larger.
Consider the Tower of Hanoi, in which a number of discs are placed on 3 pegs, each smaller than the disc below it. The goal is to move the discs from the left peg to the right peg. However, they must always be smallest on top and larger beneath. When the tower has 3 discs, it can be solved in 7 moves. However, add 1 more disc and 15 moves are needed. Add another and 31 moves are needed. Just as the Tower of Hanoi, brute force measuring gets excessively large.
The idea of recursion is a process of repeating items in a self-similar way. A very basic example of recursion is this picture of 2 bathroom mirrors facing opposite of each other. The image of myself gets repeated between these 2 mirrors over and over again. If we could zoom into these mirrors, we would still see my image being repeated forever. In mathematics and computer science, there are 2 rules that define something as recursive. First, there is a base case that ends the recursive calls, and then a set of rules that reduce all other cases toward the base case. I will demonstrate recursion by solving a maze. In this maze, 0s represent walls, 1s represent the paths, and 2s represent the exits. The way this method works is that first it checks up, right, down, then left to see if there is a 1 any direction. When a 1 is found, the method will be called again. This method will check every possible path till an exit is reached. When a dead end or an exit is reached, the current method will end, going back to the previously called method. The idea is that for every step in the maze, the same test is ran over again. This is recursion because the test is repeated in a similar way for every step in the maze.
Using the idea of recursion in Dijkstra's algorithm, we designed this program to find the shortest path between 2 vertices. This code creates an interactive window where the user can draw any graph, set values for each edge, and find the shortest path between any 2 designated vertices. The main heart of our code is our recursion method. It is this method and the one below it that allows us to recursively find the shortest path. Here is a simple example of how our program works. First, you add as many vertices as you want on the screen. Next, you draw edges in wherever you want them. After you have drawn all of your vertices and edges, you click the Set Values button and enter the values for each of the edges. After that, it will prompt you to enter a starting vertex and an ending vertex. After you enter these, it will solve your graph. Our program doesn't just work with simple graphs. Any graph you can draw on the screen, our program will compute the shortest path.
Through our inquiry of the shortest path phenomenon, we found that the best way to find the shortest path of a graph, no matter how large, is by use of recursion. We explained Dijkstra's algorithm, and the answers to our questions led us to a recursive program that finds the shortest path of a graph.